Okay, in this video we are going to talk about the Grignard reaction. This is a very useful reaction that can make carbon-carbon bonds, and the product you usually get out at the end of this reaction is an alcohol. So the first part of the Grignard reaction is to prepare the Grignard reagent. And the Grignard reagent has the formula of RMgX, so that's R, some carbon group, carbon chain, to magnesium to a halogen. And the preparation of this is actually very simple. We start with an alkyl halide, so we're going to start with some alkyl halide, and here we have our R group and our X group. When an alkyl halide is treated with magnesium, normally in ether, you get out your Grignard reagent. There it is. There's a bond from a carbon to a magnesium to a halogen. The R groups that you can have can be a primary, secondary, or tertiary alkyl group, alkyl halide. You can also have an aryl group or a vinyl group, and we'll see examples of these down here. The halogens you can use are chlorine, bromine, and iodine to get our alkyl halide. Okay, so we can have any alkyl group, primary, secondary, or tertiary alkyl halide. R can be an aromatic ring or a carbon-carbon double bond, and we call that a vinyl group. So let's just look at a couple of examples here how we prepare our Grignard reagent. So in our first example here, I'm starting with a secondary alkyl bromide. Okay, when this compound is dissolved in ether and mixed with magnesium metal, the magnesium will insert in between the carbon-bromine bond. The mechanism of this is pretty complex and involves some radical reactions, so we don't really need to go through the mechanism here. All we really need to know is that this magnesium is going to insert right in between the carbon-bromine bond. So we now have a new bond from carbon to magnesium, and then magnesium to our bromine, and this in fact is our Grignard reagent. Kind of looking into a little more detail about our Grignard reagent, this carbon-magnesium bond is a very, very polar bond. And in this case, magnesium is less electronegative than carbon, so these two electrons are not shared equally between the carbon and the magnesium. Carbon in this case is more electronegative than magnesium, so the carbon actually has a partial negative charge, whereas the magnesium has a partial plus. So here what I've done is wrote a delta, a lowercase delta, signifying that the carbon has a partial negative and the magnesium has a partial positive. Well, what we've done here is by putting a partial negative charge onto our carbon, I've created a very good nucleophile. So Grignard reagents are in fact really good nucleophiles, and that's how we're going to use this reagent to do the Grignard reaction. The next example, this is a vinyl bromide. So here's a vinyl group. A vinyl group, you have an sp2 hybridized carbon directly attached to a halogen, in this case bromine. And these compounds work exactly the same. The magnesium will insert in between this carbon-bromine bond. So now I have a carbon connected to a magnesium, and that magnesium is now connected to my bromine. And again, this is our Grignard reagent, and again, a great nucleophile. So the first example, we have a secondary alkyl halide. Here we have a vinyl bromide to form our vinyl Grignard. And the last case we can see is this also works with aromatic rings. So in this example, I could treat this with magnesium and ether to get a Grignard reagent. Alright, but I'm just going to show you another example. This is now called an organolithium compound, or an organolithium reagent, and this will react exactly the same as magnesium, as the Grignard reagent. In this case, to prepare this, you take any of these compounds would work, the secondary, the vinylic, any of those would really work. Okay, so and how this is really prepared is I take my alkyl halide, or in this case my aryl bromide, and I treat it with 2 equivalents of lithium and hexane, and a very similar process happens. The lithium will insert between the bond. 2 equivalents of lithium work, so one of the lithium forms LiBr and the other one is attached directly here. And the process is exactly the same, or the polarity of the bond is exactly the same. So this carbon that's attached to now my lithium has a partial negative. This is a very, very polar bond. And my lithium has a partial plus. And just like my Grignard reagent, this species here is also a really good nucleophile. Okay? So when I take in any alkyl halide, vinyl halide, or aryl halide, and I treat it with magnesium, I get my Grignard reagent. I can treat any of these with lithium and hexane, and you need 2 equivalents, and that forms our organolithium reagent. And all 3 of these compounds have polar bonds and are good nucleophiles. So remembering from chemistry, nucleophiles like to react with electrophiles. So now let's just take a look at some of the electrophiles that we can use to do Grignard reactions. So the first group we have here, this is an aldehyde, R carbonyl to H, that's an aldehyde. A ketone, R C double bond O to R prime. Here we have an ester, R C double bond O to OR prime, and we have an epoxide. And all of these are good electrophiles. So let's just kind of write these names down so we don't forget. Here we have an aldehyde, and I'm just going to abbreviate these. Next we have a ketone. Below that we have an ester. And below that we have an epoxide. And all of these compounds here are very good electrophiles. So what we really need to do for our nucleophiles, we've identified the nucleophilic carbon. That's the carbon attached to the magnesium, or the carbon attached to the lithium. Now we need to identify which of the carbons is electrophilic. And that's pretty easy to see when I have a carbonyl. This bond here is very polar, and you can almost think of drawing a resonance structure there. So much so that the carbon now attached to the oxygen is very electropositive, so this carbon has a partial plus, and the oxygen has a partial negative. So when we talk about the electrophilic atom is the carbon of the carbonyl, and that's the case for the aldehyde, the ketone, and the ester. So in each of these cases here at the ketone, this carbon, I'm marking in green, is electrophilic. It has a partial positive charge. Same for the ester, the carbon of the carbonyl has a partial positive charge. And looking at the epoxide here, what we can really do is, looking at our epoxide, we see we have a 3-membered ring, so there's some substantial ring strain here. So what we're going to do is really attack one of the carbon centers to open up this epoxide, and we're always going to attack the least hindered site. You can really think of this as an SN2 reaction. So anytime you have a Grignard with an epoxide, you're always going to attack the least substituted side of the carbon that's attached to the O. Okay, so here's our nucleophile. These are different electrophiles we can see. And one thing I just want to mention, there are some limitations to the Grignard reaction. And the limitation is whenever we have an acidic proton, the Grignard reaction is not going to proceed. And why that is this is a good nucleophile, but nucleophiles are always in competition to be bases. So with aldehydes, ketones, esters, and epoxide, there's no acidic hydrogens here. So these species can act as nucleophiles. However, when we have a compound that has an acidic hydrogen, like a carboxylic acid, these compounds are actually going to act as bases to deprotonate this instead of doing our Grignard reaction. Okay, what we're going to do now is really go through examples. We're going to generate some nucleophiles, add some electrophiles to see what the products we make. And what we're looking for here is to form a carbon-carbon bonds and form some alcohols. And we'll even see an example of a limitation. So let's look at a few examples here. Okay, so here is our next page. And let's look at our first example here. You can see I have an alkyl halide and then a 3-step reaction. I'm going to treat this with magnesium and ether. Step 2, I add an aldehyde, and then I'm going to do an acid workup here. Okay, one thing we really want to remember is CHO is an abbreviation for an aldehyde. So what I like to do is really cross out that O and just write a double bond to our oxygen, so we don't forget that this is in fact an aldehyde. So what we'll do in this example, let's go through the mechanism and then describe and figure out what the product we're going to have is. Okay, so looking through, the first step is we're going to treat our alkyl halide here. This is a primary alkyl bromide, and we're going to treat that with magnesium and ether. And we just saw this above. What this does is creates our Grignard reagent. Remember that the magnesium will insert between the carbon-bromine bond. So we're going to add a magnesium, and that's also connected and bonded to our bromine. And this now gives us our Grignard reagent. And again, just to remind you, this is a very, very polar bond here. And the carbon that's attached to the magnesium has a partial negative, making it a good nucleophile, and the magnesium has a partial positive charge. So in step 1 here, we've created a very good nucleophile. Now we're ready to proceed with step 2. And in step 2, the reagent we add is now an aldehyde. And remember from this example that the carbon of the carbonyl, so this carbon I just made in green, has a partial positive charge. That's got a partial plus, and that is my electrophile. So from step 1, I've created my nucleophile. Step 2, I've added my electrophile, and those are going to react. And what happens here is just exactly what you would expect. We're going to break the carbon-magnesium bond, and that is going to attack the carbon of the carbonyl. Now carbon has 4 bonds that are made, so when I form a new bond from the carbon of the nucleophile to the carbon of the electrophile, we have to break one of these double bonds. So the second arrow we see here is we break one of these, we break our pi bond, and that pi bond becomes an extra lone pair on our oxygen. So let's draw out the product that we get from this attack step. What I'm going to do here is now just draw my nucleophile, the alkyl group, 1, 2, 3, 4 carbons. Okay, so here we have 4 carbons. 1, 2, 3, 4. This carbon was connected to a magnesium, but I've now broken that bond, and it's now connected to my electrophilic carbon. So let's show our new bond in orange. So there's our new bond. And we need to now show that that is connected to our electrophile. So what I want to do in the beginning here is just label my carbons. We're going to call the carbon, that's my electrophilic carbon, carbon A, and then that's connected to carbon B and carbon C. So when we draw these out, this is my electrophilic carbon A, which is connected to carbon B and carbon C. So here we have A, B, and C. So I've now indicated my new bond. 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. I have a new bond from the nucleophilic carbon. We'll put a little dot there. There's my nucleophile. A new bond from the nucleophilic carbon to the electrophilic carbon, and that new bond is shown in orange. And the electrophile has 3 carbons, A, B, and C. The other thing we have to remember is this carbon had a double bond to an O, but now that pi bond has broken, so what's left is we now have a single bond to an oxygen. That oxygen originally had 2 lone pairs, okay, but this pi bond now became a third lone pair on this oxygen, giving this oxygen 7 valence electrons and a negative charge. So the first step here, we added magnesium to create our Grignard reagent, and we just really completed our second step where we attacked the carbon of the carbonyl of our aldehyde to make our new carbon-carbon bond and an O-. So we now get to our third step, and in our third step we are adding H3O+, and I'm just going to write that as H+, so I have to draw less arrows. And simply what we're going to do is we're simply going to protonate that O-, our alkoxide group, and that's going to give us our final product. So let's draw our final product here. 1, 2, 3, 4 carbons. Our new bond to the electrophile, which has 1, 2, 3 carbons. And now we have on that carbon an OH. And this is in fact the final product we get from this reaction, from our Grignard reaction. Okay, so what you can see we've done overall is we have made a new bond from the nucleophilic carbon here to the electrophilic carbon here, and that new bond is shown there. And this carbonyl, the C double bond O, has formed now an alcohol in OH. So that is a Grignard reaction. Now let's look at our next example here. What I want to do in this case is not go through the full mechanism, but simply predict what the product is going to be. So looking at this problem, thinking about it, I understand in step 1 I'm going to add magnesium that will insert between the carbon-magnesium bond, giving us a partial negative on this carbon, and that carbon is going to be our nucleophile, our nucleophilic atom. So I'm just going to put a red dot here because that's going to be our nucleophilic atom. Step 2, we add in our carbonyl that is our electrophile, so the carbon of the carbonyl is electrophilic. And remember, what we do is we simply make a new bond between our nucleophile and our electrophile. So on our electrophile, let's just label our carbons so we don't lose track of those. I'm going to start from the right to the left. Carbon A, B, C, and D. And now let's see if we can predict what our product was going to be. So I'm going to draw my nucleophilic carbons first. There's 3 carbons. The new bond I have is from the nucleophilic position to the electrophilic position. So there's my new bond in orange. And now what I need to do is draw in the carbon chain. So here is my electrophilic carbon our electrophilic carbon in blue. And remember that the electrophilic carbon we're attacking is carbon B. So what I've just drawn here is in fact carbon B. We see that carbon B is connected to carbon A on the right and C and D, so I need to show those connections. So carbon B is connected to carbon A, carbon C, and carbon D. So let's label these. There's carbon A connected to carbon B is connected to C, and C is connected to D. So now I've handled all of the carbon chains. Here's my new carbon-carbon bond. And the other thing we have to remember, what happens to the C double bond O? That C double bond O becomes a single bond and becomes an alcohol. So we also get attached to here in OH. Okay? So sometimes you need to go through the mechanism, but other times you're just asked to predict the product. So what we see here is we identify the nucleophilic position, we identify the electrophilic position, we form a new bond between those, okay? Alright, so we form a new bond between those. So this new bond is here, the nucleophilic to the electrophilic, and that new bond is shown in orange. And our electrophile has A, B, C, and D, and the carbon that was the carbonyl becomes an OH. And again, that is our final product for our second example. Okay? So what you can notice here is when your electrophile is an aldehyde, you get out a secondary alcohol. When your electrophile is a ketone, you get out a tertiary alcohol. Now let's look at our next example. Okay, in this case, our electrophile is an epoxide. Okay, so here's an epoxide. And in this case, I'm not doing the Grignard, right? I'm making an organolithium reagent, but it's really the same exact thing. Okay, I could do a Grignard here, but here we're doing the lithium. So what happens in step 1 is we are going to draw and make our organolithium compound, and that lithium will, in this case, replace our halogen, okay, to make an organolithium reagent. It reacts exactly like a Grignard reagent, right? Remember that the carbon has a partial negative, lithium has a partial plus, and this is a great nucleophile. So when we're looking at step 2, Step 2, we've now added an epoxide. So if we remember from our epoxide, there is some substantial ring strain here. So a nucleophile can come and open up this epoxide. Now we have a choice between which carbon to attack, the carbon on the left or the right, and we're always going to choose the carbon that's least hindered, the carbon that has more hydrogens. This carbon has 2 hydrogens here. This carbon is attached to 1 carbon and a hydrogen. So the electrophilic position that we are going to choose is this carbon right there. So what I want to do now, again, is label my carbons A, B, and C. And let's draw our mechanism here. So our nucleophile, we're going to break this carbon-lithium bond, and we're simply going to attack carbon A. Again, carbon A has 4 bonds, so now we have to break a bond, and what we're going to do is break the carbon-oxygen bond to alleviate strain. So when you attack an epoxide, you attack the least hindered carbon that's attached to the O, in this case A, and I break the carbon-oxygen bond that's connected to A. So let's see what the consequence of that is. So here I'm going to draw in my carbon chain. Again, we have 4 carbons. Next, I'm drawing in my new bond in orange. And then I'm going to draw in my 3 bonds from the epoxide. And we're going to label these here A, B, and C. So counting carbons, 1, 2, 3, 4, 1, 2, 3, 4, 4 in our nucleophile, 1, 2, 3, 4. Our epoxide has 3, our electrophile, 1, 2, 3, A, B, C. And what we now have to remember is we still have an oxygen. But in this case, because we attacked the carbon labeled with an A, I've broken the bond from carbon A to the O. So there is no oxygen bond here. What I haven't touched is the carbon-oxygen bond that's attached to B. So with the epoxide, let's just erase this B a little bit and move it over so we have more room. There's carbon B. What we have now is this bond between carbon B and O is still there. And we're going to draw that in. So that oxygen will again have 3 lone pairs, right? The original epoxide had 2 lone pairs. The 2 electrons from the bond between carbon A and O now became our 3rd lone pair, giving this oxygen a negative charge. Okay, we're only 1 step away from finishing our mechanism, and that's our 3rd step. And in our 3rd step, what we're doing is, again, doing an aqueous workup or an acidic workup, adding an H plus or H3O plus, and what I like to do is just write H plus. So that extra electron, the alkoxide, will attack our H plus to give us our final product. 1, 2, 3, 4 carbons. Now we attach to our electrophile. Boom, boom, 3 carbons are electrophile, and we have our OH. Okay, so comparing and contrasting these 3 reactions, here we have a Grignard with an aldehyde. Nucleophile attacks electrophile, we get a new bond with the alcohol. So the OH is attached to the carbon that was the original electrophilic carbon. Same with the ketone. Here we attack carbon B. B is still connected to A and C and D, but the new bond is connected to the carbon that has an OH. The epoxide is different. When we attack an epoxide, I break the carbon-oxygen bond at A, so what's left is my alcohol is 1 carbon away from the original electrophilic carbon. Okay, looking at our final product here, this is carbon A. That was attacked, but that bond broke in this step, so my alcohol is 1 carbon away on carbon B. Okay, so those are the products we get from our Grignard reaction with an aldehyde, a ketone, and an epoxide. Okay, we have a couple more examples to look at here. In our next example, we are now going to look at a Grignard reagent reacting with an ester. And if you notice in this case, I have my ester, my electrophile, as a reactant, and my Grignard is a Grignard reagent as a reagent. So I'm not making the Grignard reagent; it's already provided for you, and that's fine. doesn't matter where they are. So let's go through the mechanism of this process. Just to remember, the carbon of the carbonyl is electrophilic, so we'll put a little blue dot here as electrophile. And we remember that our Grignard reagent has a partial positive charge and a partial negative charge. So this carbon is nucleophilic. So what we can do in our first step of the mechanism is our nucleophile is going to attack the carbon of the carbonyl and push up that pi bond to be a lone pair on the O. So I will draw out our electrophile. The double bond has now become a single bond, so this carbon is still connected to an oxygen, and now that oxygen that had 2 lone pairs, that oxygen now has 3 lone pairs. This carbon atom is still connected to the methoxide group, the OMe, so we need to draw that in. And finally we can add our new bond, and there's the new bond we're making. So essentially what we've done is we made a new bond from this carbon to that carbon, and that's shown in orange. This is still connected to the propyl group, an O and an OMe, and our nucleophile had 2 carbons, so we just need to add those 2 carbons. There's carbon 1 and carbon 2. Okay, so this is the first intermediate we made. It is the first step we see when you react a Grignard reagent with an electrophile of a carbonyl. What's special about this case, and what's special about esters, it does not apply to aldehydes or ketones, just esters, is that this species is unstable. Having an O- and an OMe here is unstable. So instead of protonating and finishing the reaction, something interesting happens. A lone pair from the oxygen will actually come back down to reform our double bond, breaking this carbon-oxygen bond. So what that gives us now is we reform our double bond, so we now have again a C double bond O that has formed. So this is the intermediate that we get. What you should notice is that this is a ketone, and we have a Grignard reagent in the presence of a ketone. So what happens next here, and you notice I wrote excess here, is that a second equivalent of our Grignard reagent will actually now react with this ketone. So I'm going to redraw a second equivalent, circle the nucleophilic position, and again we attack the carbon of the carbonyl. Okay, so what we get resulting from that is, again, now we have our single bond to an O-. Here's our original nucleophile that attacked, and now we have a second nucleophile that attacked as well. So with an ester, the nucleophile attacks once, this intermediate will come back to reform our double bond, and the nucleophile, a second equivalent, will attack again. So I've added 2 nucleophiles, 2 ethyl groups, to the ester. The final step is just like every other step. Okay, so we can add in our H+, do our H+ workup, our acidic workup, to now simply protonate that O- to give us our final product. Here's the electrophilic carbons, that C double bond O has now become an OH, and our nucleophile has added twice. So with an ester, we get out now a tertiary alcohol. So it's important to remember here, this is a specific example. Anytime you see an ester, you have to remember that your nucleophile adds twice. It adds 2 times. Okay? That never happens with the aldehyde. It never happens with a ketone or an epoxide. Only with an ester. Okay, the next thing we're going to do is we're going to actually look at that limitation I told you about. So in fact, this bottom reaction here is not going to undergo a Grignard reaction. And what I want to do is just point out again, here I have a partial negative and a partial plus. Okay? So, the carbon of the carbonyl is electrophilic. The carbon of the Grignard reagent is nucleophilic. But there is one issue here, is in this case we have an acidic hydrogen. So every other example we didn't have any acidic hydrogens. Here we do. Nucleophiles are always in competition as acting as bases. So when there's not any acidic protons around, our Grignard reagent acts as a nucleophile. But a carboxylic acid is an acid. So the reaction is going to be much faster where I take this H away, or I deprotonate this H. So let's just draw this H out, just so we can show the mechanism of what actually happens here. So now instead of attacking our electrophile, what happens is you actually simply deprotonate the carboxylic acid. So we do not undergo a Grignard reaction. We're simply doing an acid-base reaction. And this is not something that's useful for us. You don't want to use a Grignard reagent to do this. And the other product we get out is in fact just ethane. Okay, so if you look, I have 2 carbons here. This bond breaks to form a new bond to H. So the other product that I see here is simply ethane. Just so we're not confused, we'll draw our H's here. So when you're running the Grignard reaction, the Grignard reagent is not compatible with acidic hydrogens. It's not compatible with carboxylic acids. So really 2 important cases here. Esters, the nucleophile adds twice because this species is unstable, and carboxylic acids are not compatible. You do not do the Grignard reaction here. The Grignard reagent will simply deprotonate that to get our species here. Okay, let's look at one more example here, one more question. Here I'm giving you a molecule. This is a tertiary alcohol. And what I want to do is just figure out a way, 2 ways to actually synthesize this. So now we're thinking about our reaction backwards. So if you remember, the new bonds we're making when we're running our Grignard reaction is we're always making a new bond to the carbon of the alcohol. Okay? So this carbon that's connected to the alcohol as our final product is the electrophilic carbon. So thinking about that, there are a couple of options on where we can form our new carbon-carbon bond. I'm going to show you all three bonds that we could make, thinking backwards. So I could make a new bond here. I could make a new bond here, or I could make a new bond there. So let's do our example in red. Okay, if I make this new bond here, that's one piece, and that's the other piece. So the new bond that's formed is between here and here. So how can we synthesize this compound? Okay. Well, what we can do is which side is going to act as the nucleophile. This will be the nucleophilic carbon because the carbon in blue is the electrophilic carbon. So in this case we have 1, 2, 3 carbons. So if we have 1, 2, 3 carbons, how do we make that carbon nucleophilic? Well, we make it from a Grignard reagent. Grignard reagents are made from alkyl halides. So I'm going to start with an alkyl halide with 3 carbons. My first step will be to make the Grignard reagent. And again, in here, you usually do this in ether. I'm not going to write it. So we've gotten this piece taken care of. Okay. Now what we need to do is think about the other piece on the right. What is the electrophilic carbon? It's not a C as a single bond to an O, it's actually a carbon as a double bond. So thinking backwards here, there's not an H here, there's actually a double bond there. So what type of compound do we have? 1, 2, 3, 4 carbons. Let's just erase this to give ourselves a little more room to write. There we go, that's a little cleaner. So remember, this is going to be a double bond, there won't be an H here, and our electrophile, A, B, C, D, has 4 carbons with a double bond connected to carbon B. So step 2 is simply a ketone. That's our electrophile. And the third step, of course, we have is our H+ workup. Okay, so what we have here is one pathway to synthesize that compound. So let's put that as an answer here. Alright, originally I asked you to do this 2 different ways, so let's erase again. So we have a clear set. So the first pathway we took is we broke that bond there. Now I'm going to take a different path and I'm going to break this bond. Again, what that does is that makes this the electrophilic carbon, and that makes this piece in red the nucleophilic carbon. So here's one piece, one carbon, as the nucleophile, and the rest of this is my electrophile. So a second way to make this, and really there's 3. What I'm going to do in this case is I'm actually just going to draw the electrophile, so let's count our carbons. 1, 2, 3, 4, 5, 6. So here I have 6 carbons. 1, 2, 3, 4, 5, 6. And remember, that's the electrophilic carbon. 1, 2, 3, the 4th carbon from the right. So we'll just put a little dot here. That's our electrophilic carbon right there. And remember, our electrophile is not an alcohol, it is in fact a carbonyl. So all I need to do here is draw a carbonyl. And that is my electrophile. What is my nucleophile? Remember, our nucleophile is our Grignard reagent. How many carbons do we have here? 1, and that's fine. So our Grignard reagent, so in this case I don't have to make the Grignard, I'm just going to use it, is 1 carbon, CH3 MgBr, ethyl magnesium bromide, and that is the Grignard reagent I use to make this. And then of course we always have to end with a workup step, H+. So this is the second way I can make that compound. So 2 different ways to synthesize this compound, and clearly you can see the third way to make this is to break this bond here and add our ethyl group again to a ketone. So 2 ways to make this. Okay, basically, hopefully you have a good understanding of the Grignard reagent and the Grignard reaction. The homework I want you to turn in for Wednesday is I want you to work on these 2 problems. Okay, we'll call this problem 1 and problem 2. And what I want you to do here is simply predict the product. That's all we have to do. So in the first reaction we have a vinyl bromide, treat it with magnesium. This compound, CO2Me, remember is an ester, and then acidic workup. Second compound, we flipped it, we have our electrophile as our reagent. This is a ketone, treat that with a Grignard and work that up. So all I want you to do here is provide the 2 products that you get out from these reactions to show that you have a basic understanding of the chemistry of the Grignard reaction.